Okay, so in this problem, we got that a photographer is taking a picture of a painting hung in an art gallery, and the height of the painting is 4 feet, which you can see over here. And then the camera lens is 1 foot below the lower edge of the painting, so shown here. And the question is, how far should the camera be from the painting to maximize the angle subtended by the camera lens? Okay, so first let's make it clear what we're trying to figure out in this diagram. So we have an angle beta shown here, and then we have the angle omega, which goes all the way from here to here. Then we have the smaller angle alpha, which is just this part. An entire triangle, let me trace it out just to make sure it's clear. And it's a right triangle. Here is 1 foot, and that's 4 feet. And X is represented as like the base of this right triangle. So we want to maximize the angle beta. That's our goal. Because that's the angle that this camera lens is going to be, basically taking a picture of. And now beta, though, is equal to theta, the blue angle, minus the green angle. It's equal to theta minus alpha. And then these angles are all functions of X. So we want to find a way to represent beta in terms of X. Then we differentiate that equation and find the maximum of that equation. So let's first define the angles theta and alpha in terms of X. And for that, we're going to use the cotangent function. So then the cotangent of theta, it'll be the opposite side over the adjacent side over the opposite side. So for theta, the adjacent side is X, and the opposite side is this whole length. So it's going to be 4 plus 1, so this whole length. So it'll be 5. Now, remember, we need to get theta. So what we can do is take the arc cotangent of the cotangent. Because if you take the arc cotangent of the cotangent of theta, that just leaves us with theta. And we then are taking the arc cotangent of the right side as well. So theta is equal to the arc cotangent of X over 5. Now alpha, we're also going to use the cotangent of alpha to solve for a function of alpha in terms of X. Oops. So the cotangent of alpha, adjacent side over the opposite side of alpha. So for this green angle alpha, the adjacent side will just be the X again. And the opposite side is just a small part of this whole entire side, which is just the one part. It'll just be X over 1. And again, using that same thing we did for the cotangent of theta to get theta, we're going to take the arc cotangent of alpha, because that will just leave us with alpha, and we take the arc cotangent of X over 1. So this will be equal to the arc cotangent of just X. Then we can just set this equation equal to the arc cotangent of X over 5 minus the arc cotangent of x. This will be our equation for beta in terms of x. So then we're going to now differentiate beta with respect to x. So we want to find dB d theta, or dB dx. And then, so we just have to find the derivative of this side. And we're just going to use the, the equations for the derivatives of the inverse trig functions. So we're going to take the derivative of the arc cotangent of x over 5. And using the formula, we'll have the derivative of the inside, the derivative of negative x over 5, which is just negative 1/5, over 1 plus the inside squared, because 1 plus u squared, so to speak. So 1 plus x over 5 squared. So 1 plus x squared over 25. Minus the derivative of just x, or sorry, the derivative of the arc cotangent of x. No u substitution here. So the top then would just be a negative 1 over 1 plus x squared. Now all we're going to do here is let's kind of simplify this as best as we can so we can combine them. So what I'm going to do for that first one, I'm going to multiply by 25 over 1 times 25 over 1. Times that whole thing. So times negative 1/5 on top over 1 plus x squared over 25. Plus, because that's already minus minus, so plus a 1 over 1 plus x squared. Okay, and I'm just doing some fancy algebra. You don't have to, and again, you don't have to simplify this way, but breaking it down, you'll get a negative 5 on top. And here you'll get 25 plus x squared. And then plus, I'm going to leave a space here, you'll see in a second, plus 1 over 1 plus x squared. And then to combine these two guys, you're going to want to multiply this by 25 plus x squared over 25 plus x squared. And this one, you're going to multiply by 1 plus x squared over 1 plus x squared. And then so the whole thing will be all over 25 plus x squared times 1 plus x squared, all over a negative 5 plus 25, or positive 20, I guess, which will be a positive 20. And then negative 5 times an x squared, so negative 5x, plus a 1 times x squared, so 20 minus 4x squared. Okay, so this is our equation for the derivative of beta. So since we're trying to maximize beta, we got to find critical values of this and then see what's going on with the function before the critical value and after to see that we can get a local max there. So we're going to set the top to equal to 0. because the bottom's always going to be positive, so it's not going to be undefined anywhere on this domain at least. So again, we're essentially solving for d beta dx equal to 0. So setting the denominator equal to 0, or setting the numerator equal to 0 is what I meant. You got 0 equals negative 4x squared plus 20. And solving this, we'll get that x squared will be 5. And then x is going to be the square root of 5, since x can only be positive. Okay, so then we want to then figure out what's going on before this value and after. So again, drawing like a number line. Here we got that x is root 5. And then we want to see what the graph here looks like. Like what's the sign of d beta dx before this value and after? So let's figure it out as 0. And then let's just pick a number after. Let's just pick 10 because that's easy to evaluate. So we're going to figure out what db dx is when x is 0. And then what db d theta is, or db dx is when x is 10. So we just got to plug those into our equation for the derivative. So just going back to this. So we'll just get 20 minus 0 over 25 times 1. So we just get 20 over 25. Or actually, sorry, I forgot the other part. Well, no, I got that right. And again, what matters most is that the sign of this. This is a positive number. So if we know the derivative is positive, we know the graph is going up before then. And then at db dx, when x is 10, we plug 10 into our equation. We'll have 20 minus 400 over 25 plus 100 over 1 plus 100. So our derivative will look like this. Now the top, again, we know this is going to be negative and the bottom will be positive. So this will be 0. So the derivative at this point is negative. So then the derivative means that the graph is going down. So then we do get a maximum at x equals the square root of 5. And then so that means that's going to give us the largest angle, beta. And let's go ahead, let's just summarize that. So the local max occurs when x equals the square root of 5. We're using our calculator. I think it will be about 2.2, I believe. Yeah, about 2.234. 2.234 feet. So that's how far away they're going to want to place the camera lens. And the angle that it'll get, we can figure that out by taking beta of this value, beta of x, or the beta of the square root of 5. That'll be equal to the arc cotangent of root 5 over 5 minus the arc cotangent of root 5. And then you'll get about 0.7297 radians. Or you can, in degrees, they'll be about 41.81 degrees. All right, so that's a good problem to really apply this stuff. So I hope that helps, and good luck.